This is a gate problem from the analog electronics module, and looking at the circuit we can find that this is a combination of concepts from the bipolar junction transistor as also that of the ideal operational amplifier. So here is the problem statement. Assuming base to emitter voltage of 0.7 volt and beta equal to 99 of transistor Q1, the output voltage V0 in the ideal op-amp circuit shown is option A negative 1 volt, option B negative 1 by 3.3 volt, option C 0 volt, and option D is 2 volt. So with this given circuit, let us see what are the information that we already know. So if we look at this operational amplifier, and based on the fact that this is an ideal operational amplifier, we can use the concept of virtual short and note that if the voltage to the non-inverting input is 1 volt, then the voltage to the inverting input terminal will be the same. So voltage at this node will also be 1 volt with respect to ground. Secondly, we are given a 100 ohm resistance, and here is a 33 kilo ohm resistance. So just like my previous videos, here also we will make the same substitution where we will convert this ohm into its kilo ohm format. So this 100 ohm resistance can be represented as 0.1 kilo ohm, and therefore all the currents in the circuit will turn out to be in milliamperes. Next, we are given the base to emitter voltage of 0.7 volt, so we know that this drop will be plus minus 0.7 volt. And if we consider this to be a base current of IB value, then the emitter current is beta plus 1 times IB. And since beta is equal to 99, therefore beta plus 1 will be equal to 100. And so the emitter current is 100 times IB. Now note that this emitter current 100 IB cannot flow into the input terminal of the op-amp because this is an ideal op-amp and it offers infinite resistance, input resistance. And so this 100 times IB current will flow through this 0.1 kilo ohm resistance and then enter through the output terminal of the op-amp. So these are the basic considerations that are possible to make based on the information that has been provided in the question, and our ultimate objective is to find out this value of V0. And what we can do is we can first of all try to identify what should be the value of this base current IB, because once we can find out the base current IB, it is easy to show that we can easily find out the value of V0 using Ohm's law for this particular resistance. So how do we find out IB? We can use this loop, this particular loop, to evaluate the value of IB. So let's see, this is negative 5 volts plus 33 multiplied by IB plus 0.7 plus 1 volt, which should be equal to 0. Note that the voltage at this node, which occurs due to virtual short and that has a value of 1 volt, is with respect to ground. So we end our equation right over here. So all this summation should equal to 0 as far as KVL is concerned. And if we find out the value of IB from this equation, IB turns out to be 0.1 milliampere. Next, this current is 100 times IB, and so the voltage between these two nodes can be written as 1 minus V0 divided by 0.1 kilo ohms should result in this current. And therefore, using the concept of Ohm's law, we can write that this current, which is 100 times IB, is equal to 1 minus of V naught divided by 0.1. And if we do this little math, V naught turns out to be 0 volt. So the answer to this problem is option C, which is equal to 0 volt. So this question was testing our understanding of the basic relation for a BJT current, where the emitter current is equal to beta plus 1 times IB. And then the basic concept of an operational amplifier. In an ideal mode, the voltage at the non-inverting input terminal is the same as the voltage at the inverting input terminal. Note that we had no use on finding out the voltage between the collector and emitter, or in a sense, this 5-volt source did not come into play in our circuit equation. But there could be a follow-up question to this problem, and the follow-up question would be that can you find out what is the power dissipation of this transistor? So power dissipation is given by the collector to emitter voltage drop multiplied by the collector current. And so because we have found out the base current, so base current is equal to 0.1 milliampere, the collector current would be equal to 0.99 milliamp. It will be 9.9 milliamperes, because we are multiplying 0.1 multiplied by 99. So collector current will be 9.9 milliamperes, and then the collector to emitter voltage drop will be 4 volt, because at the collector terminal we have 5 volt, at the emitter terminal we have 1 volt, and therefore VCE is equal to 4 volt. Therefore the power dissipated by this transistor will be 4 volt multiplied by 9.9 milliamperes. So later on in this course, we will look at more questions like so, where there could be combinations of a bipolar junction transistor and an op-amp, or a MOSFET and an operational amplifier in combination with Zener diodes or normal silicon diodes also.